Notes are on centripetal force, gravity, and magnetism. Magnetism is a force of attraction between two special objects. Those objects have properties that draw other objects to them, and this force acts like gravity. Magnetism is a force you can't see. However, you can see the objects moving towards or away from each other, and the objects do not need to be touching. So how do magnets work? Magnets have atoms inside of them. These atoms have electrons that spin in different directions. So very simply put, the direction that these electrons spin causes a magnet. So a magnet is caused by the spinning of electrons. The arrows below are pointing in the direction of the spin of the electrons. Notice that the magnet has all of the arrows going in the same direction. So if you look here, okay, the arrows are pointing this way into the south side of a magnet, and they're going in the same direction outside of the north side of the magnet. Okay, same with this magnet over here. The arrows are all going in the same direction. That means that all the electrons are going in the same direction in this magnet. Usually they would spin towards the north end of the magnet. The arrows of an object that is not magnetic are facing in many different directions. So you can take a nail and you can actually magnetize it or make a magnet out of a nail. You might have done this maybe with like a paper clip before, or maybe even a nail. But generally an unmagnetized nail is going to look like this. If you look inside, the arrows are pointing in all different directions, okay? They're all kind of in an unorderly fashion. If you look at the magnetized nail, they're all going in a nice, even, equal direction. Electron spins or poles that are the same and facing one another repel, and poles that are opposite and facing one another attract. So opposite poles attract, so south and north are going to attract. They're going to stick together, and same poles repel. They're going to push away from each other. So the attraction is like a pulling force, and the repelling is like a pushing force. Okay, so south and south are going to repel, north and north are going to repel. South and north will attract. They will stick together. Magnets have invisible lines of force. They are forces that attract other magnets. You can make a map of these forces. So if we were in school right now, I would take a magnet and I would drop it in the middle of a pile of iron filings, which are just little tiny pieces of iron. They look like, little pieces of dirt almost. And you would actually see the iron filings make these lines of force. Okay, and they would look pretty similar to what you see in this picture. Like poles, again, repel or they push away, and opposite poles attract or pull together. So if you had these iron filings, north and north pole coming together, you can see the iron filings are trying to get away from each other. They're showing how the two like poles repel. Okay, and then if you have a north pole and a south pole, opposite ends, they're going to pull together, and you can show that the filings are attracted to one another and they want to stick together. Okay, same thing here. You have two magnets here, north end close to a south end, which means they're going to attract. And if you look, okay, the lines are all going, the arrows are all going in the same direction around the magnet from south to north, or from north to south, sorry. North to south, and then here, same thing, north to south. And you can see them, the force of attraction really strong in between, and then the like poles repelling north to south and north to south. They're going in the opposite direction. What happens when you break a magnet? So if you break a magnet in half, you would have two smaller magnets all with north and south poles. So if you break a magnet, say you take this magnet and break it in half, it's not like you get just a south magnet and a north magnet. You get two magnets now with a south and north side. Okay, so you can see that down here. We break it in half. Now we have two magnets. We break each of those halves into half, and we have four magnets, each with a north and south side. A magnet is going to be strongest at its poles or at the very end. And again, this is what it would look like if we took a magnet and dropped it in a bunch of iron filings. You would get this design, okay? And you can see the force lines outlined here. If you move a magnet along a needle or a nail or a paper clip in the same direction, you can actually take the electrons and line them up so they're spinning in the same direction to create a temporary magnet. So this magnet isn't going to be permanent, but it'll last for a little while. So if you magnetize a nail, you can actually pick up something else that is magnetic, like a paper clip. These two items wouldn't be magnetic on their own, but when you magnetize one of them, then the other one will stick. You can also destroy a magnet. This is why you're supposed to keep your cell phones away from like hotel room card keys. You know, those things that the cards that you use to get into your hotel rooms. Those have a magnetized strip on them, and a cell phone will ruin it, and you won't be able to get into your hotel room. So you're destroying the magnet, basically. So you can heat a magnet, and that'll move the molecules enough that it destroys the magnet. You could drop it hard enough, and it will move the molecules enough to destroy it. And also you can use another magnet to undo the magnetic domain. So that's like what a cell phone does. Okay, just a joke. If you remember back to the rocks and minerals lab when we tested the minerals for magnetism, lodestone is a naturally magnetic substance, so that actually acts as a magnet, and things that are magnetic will stick to it. Magnetite is also another natural magnetic substance. Iron, cobalt, nickel, and steel are attracted to magnets. So metals that contain iron, cobalt, nickel, and steel are attracted to magnets. Moving on to the force of gravity. The law of gravity, the amount of gravity between any two objects depends on their mass and the distance between them. So what does this mean? There is gravity between each and every object in the universe. There's a force of attraction between the truck and the butterfly. So any object in this universe, there's gravity between. So there's gravity between you and your chair right now, you and your Chromebook, you and your cell phone and the table, your cell phone and the refrigerator, okay? Any objects in the universe, there's gravity between. So there's also gravity, again, between a student and his or her pencil, but when you drop a pencil, it doesn't move towards you, okay? So if there's gravity between you and things, how come when you drop things, they don't move towards you? And this is because if you look at the Earth and your pencil, the Earth has way more mass than you do, so gravity is going to pull your pencil to the Earth and not to you. So the Earth is enormous, it's huge. That's why every single thing that you drop or that can fall down a ramp or anything, it's going to move towards the center of the earth because the gravity is so strong. So the law of gravity, gravitational force depends on the mass of each object and the distance between them. So a large mass equals a large gravity. So this is known as a direct relationship where one factor increases and the other will also increase. So if mass of an object increases, so will the amount of gravity. So let's consider the moon and the earth and the differences of their masses. So the earth's mass is 5.97 times 10 to the 24th kilograms. It's enormous. And the moon's mass is much smaller, 7.36 times 10 to the 22nd kilograms. So, and then the sun, as you know, is even bigger than the earth and the moon, right? And that's why when we talked about tides a few units ago, remember we talked about tides and how the moon has a bigger effect on the tides than the sun does. Okay, even though the sun's way, way, way bigger than the moon is a lot closer, so we'll talk about that too. So the moon is a sixth of the mass of the earth and it has 1/6 of the gravity. So if you're 60 Newton weight on earth, you're 10 Newton weight on the moon. So the moon barely has any gravity. It does have some gravity, but that's why you're virtually weightless on the moon, because of gravity. So this is what I started talking about with the sun and tides. Distance also affects the amount of gravity, so the larger the distance, the less gravity. So the more distance between objects, the less gravity. So if there's a small distance, if objects are close together, gravity is going to be larger. So when one factor increases, the other decreases, and this is called an indirect relationship. So a direct relationship is when one factor increases, the other one also increases. An indirect relationship is when one increases but the other decreases. So as distance between objects increases, gravity is going to decrease. So that is why the moon has a greater effect on tides than the sun, because even though the sun is 1,000,000 times, more than 1,000,000 times larger than the moon, it's huge, it's enormous, the sun is way, way, way farther away from the earth than the moon is. So the gravity between the earth and the moon is what causes the biggest change in tides. Gravity provides the weight of something. So remember, weight is actually a force. So gravity, the force of gravity, has an effect on the mass of objects, okay, including you. Okay, so weight is a force. So how do you find out just how much weight you have? To find out your weight or force, you take your mass in kilograms times acceleration due to gravity, which is 9.8 meters per second squared. Thankfully, a scale does that for you. So when you step on a scale, they're doing that calculation. They're taking your mass in kilograms, or the scale is taking your mass in kilograms and multiplying it by acceleration due to gravity, which is 9.8 meters per second squared. So it takes the force of gravity and multiplies it by your overall mass. Your bathroom scale does the same thing, only it uses 32 feet per second squared and gives you your results in pounds. So generally we do our weight in pounds here, but it could also be done in kilograms. So we didn't get a chance to use spring scales. Spring scales are tools that measure the weight of objects by what you do is you hook an object on the end of this scale, okay, on this little hook here, and you hold it up, and how much it pulls down, it moves this little scale here, and you can find out the weight of whatever object you're trying to measure. So it takes the mass of an object and multiplies it by gravitational acceleration. So virtually it does the same thing as a regular scale. So if an object has a mass of 0.71 kilograms, it would multiply it by 9.8, so you would get the weight of an object. So can you calculate the weight of a block in newtons? So they give you the mass of a block, which is 43.7 grams. The first thing you have to do is change grams to kilograms, and then you have to multiply that number by gravitational acceleration, which is 9.8 meters per second squared. So if you remember from a way, way long time ago, in order to change 43.7 grams into kilograms, you have to move the decimal point 3 places to the left or divide that number by 1,000, and you get 0.0437 kilograms. Then you use the equation force equals mass times acceleration, right? We're trying to find the weight of the block, or gravity's effect on the mass, right? And force, remember, weight is a force, okay? So you take the mass that you just found and you multiply it by acceleration due to gravity, which is 9.8 meters per second squared, and you get an answer of, a rounded answer of 0.4 newtons. The law of gravity again, just to review, the amount of gravity between any two objects depends on their mass and the distance between them. The greater the mass, the greater the gravity. The greater the distance, the less the gravity, okay? The closer two objects are together, the greater the gravity. The farther apart they are, the less gravity there is. A couple other forces we're going to talk about. One, centripetal force. You might have heard this before. This is an inward force that keeps an object moving in a circle. So, if you have like something attached to a string that you're swinging around your head, okay, that force called centripetal force is keeping that object moving in a circle, okay? There's also a force called centrifugal force, okay? So they're obviously different. One, centripetal force is an inward force, okay? It points inward to the center of rotation and it keeps objects going in a circle. Whereas centrifugal force is an outward force, okay? And that depends on inertia. So remember how inertia, objects in motion want to stay in motion unless acted on by an outside force? Well, if you're swinging around in a circle and all of a sudden you let go, that object's going to go flying, right? So that's centrifugal force. So centripetal force is an inward motion and it keeps things going in a circle, whereas centrifugal force is inertia's effect, which is where if you let go of the object, it's going to go flying out because it wants to keep moving in the direction that it was going. Again, inertia is a property of matter that keeps an object moving in a straight line, right? Inertia says an object in motion is going to remain in motion unless acted on by an outside force. All these amusement park ride pictures that are in this slideshow, a lot of these have to do with centripetal force. Going around a corner when you're driving, right? You can feel the effects of inertia. If, you're in the passenger seat of a car and someone's driving around a curve really fast, your body kind of moves towards one direction or the other depending on which way around the curve you're going. That's inertia. Track and field, the hammer throw, other examples.